Okay, rather than explaining this very long title, today what I'm going to talk about is sharing a lot of data that we've collected in the past year and a half, looking at the differentiation between immersion fluids. It's a question that's been asked a lot during the calls, and honestly, it's very confusing. I didn't honestly plan on bringing any props today, but this is actually very convenient. What is the difference between these fluids? And it's very confusing for anyone that isn't in the fluids industry or is new to this or is trying to set up some sort of deployment, gain some sort of validation. And so really our motivation, how do we differentiate between them? And then how do we validate our setup for our customers? Whether you're trying to deploy in different regions, whether you're trying to use different fluids that meet different regulatory concerns, these are questions that need to be answered before anything is put out there. And it's something that we aim to address. And so we're going to be sharing a lot of data today. Obviously, you're welcome to take pictures, but I would really encourage you to reach out after the talk, and I'd be more than willing to share all of these slides with you. Really, try and take away some of the insights. The data will be available later. So to jump right in, this is the test stand that we built. And the aim was to be capable of providing as broad a condition set as possible. So that's flow rate, that's temperatures, TTV powers. It can be interchangeable between a natural convection and a forced convection setup. And all of this we connect into, we have an internal, it's very similar to the lab view in terms of data controls and recording. So all of this is automated, and a test can take about 8 hours for one fluid, and we'll go through a pretty enormous condition set that I'll show you on the next slide. Now the types of testing that we do, obviously up front, is the fluid-to-fluid comparison, but again, we're also looking at, what about different kinds of heat sinks? We had some new targeted flow heat sinks come out. There are immersion heat sinks, there are air heat sinks. What about different TIMs? Indium foil's used all the time, but there are different types of epoxies and greases that could be used, that might be immersion ready. So how do we benchmark those? Of course, the maximum TDP question. What's the ceiling? Can we break it? Can we show the world that we're better than the 400 watts that some people think we are? Of course, durability and reliability. We can run this test for months or years even. And then finally, we run a test which I like to call the operational envelope. And what that's looking at is what condition sets are in scope, what condition sets are out of scope for a particular deployment. So mostly what targeted fluid temperature do you have to reach to ensure the IT equipment is properly cooled? So one thing I want to point out, since I have the pictures right now in front of me, are the natural versus forced convection setup. I'll be referring to these later. Natural convection is going to be similar to what you might see in most typical deployments today, in which the fluid's coming up from the bottom, it's evenly dispersed, but it doesn't necessarily go directly to the heatsink or the hot components. Instead, most of that flow is buoyancy driven from the heat that comes out from the chip. This is opposed to the forced convection setup or directed flow, targeted flow, forced flow. There are lots of terms there, but this is the inlet being plumbed directly to the hottest components. The other thing I want to mention is that we set all of our conditions for a steady state for 5 minutes. So you're not going to see any error bars or anything on the data today, but we set everything so that it doesn't move more than 1%. On the TTV itself, no more than 0.5%. So no error bars, but keep those two terms in mind when you're thinking about sort of the repeatability and the reliability of the data. All right, so this is our condition set or our test matrix. As you can see, is actually quite broad. So we do both the natural and the forced convection, many different flow rates, many different bulk fluid temperatures, and then different TTV power settings. So we cycle through this entire parametric data set. On top of that, we're showing 8 fluids today. These are a ballpark, if you will, or a good smattering of the immersion space today. It doesn't necessarily represent everything, but it is probably pretty good bookends in terms of what you might actually see. And then what are the comparisons that we're going to be making? Fluid to fluid, but we're also going to look at the difference between natural and forced convection. The use of an air heat sink versus an immersion heat sink, right? Is it worth that evolution of swapping out the heat sinks in order to gain the better performance? What ROI might you actually see on that? Of course, the fluid benchmarking, but what is the effect of flow rate? We all need to size our pumps appropriately in the tank to deliver the right amount of flow, but we don't want to overdo it because we want to maintain a low PUE. And then finally, the bulk fluid temperature, what are we looking at in terms of an operational envelope? All right, so first data set, as I said, it's pretty dense. We're looking at natural convection with an immersion heat sink. And so when I say an immersion heat sink, very generically, a wider pitch, thicker fin spacing, that really enables the oil to move through the heat sink a little bit better. And as you can see, it really is a viscosity ladder. The highest viscosity fluids aren't necessarily performing quite as well as the lower viscosity fluids. Where this has an effect, though, is, like I said before, in terms of regional deployments, different regions of the globe are going to have different requirements in terms of the flash point of the fluid. That's necessarily going to impact the viscosity that you can use. And so we need to understand, what is the differentiation in the thermal performance between these types of fluids so that we can adapt our systems appropriately. So we can see as much as 25% difference. So, for those of you who may think that, these are necessarily all interchangeable, they're not, unfortunately. So it's very important that we document this and we quantify it so that we understand what the actual performance of our system is going to be. So next, we're looking at the same data set, the same test, but a little bit cast in different light here. Now we're looking at what is the maximum TDP, right? This is sort of in aid of what's the ceiling. And there are a lot of great demos out there showing new forced convection setups in which we can direct as much flow as possible. But this is, again, returning to that natural convection setup. There's no directed flow here. And we can actually still reach over 700 watts. So that's pretty impressive. You think about what some of the TDPs are on some of the highest GPUs today, and you're meeting that barrier. And what I'll also add on top of that is that this heatsink is by no means optimized. It is an immersion heatsink in terms of wider fin spacing, but there's a lot of work to still be done in that space in terms of optimizing, perhaps the fin spacing based off of the viscosity of the fluid. So again, we see that impact, though, of the high viscosity fluids and their lower performance. It's by no means a red flag for immersion, right? 650 watts is still a tremendous result. But we also do see that temperature is king. The lower temperature that you can operate the fluid at, the more performance you're going to get. Another point I want to make is what I'm showing here on the right side is case thermal resistance. For those of you who needs a small reminder, case thermal resistance is sort of the top of the chip, and then it goes up through the heat sink to the fluid. So that's that thermal resistance. It doesn't go all the way necessarily down to the junction. All right. So last time with the same data set. Now we're looking at natural convection with an immersion heat sink, and now we're looking at the effect of flow rate. As you might expect, it actually doesn't do much. So with the flow coming into the bottom and dispersing, right, it's going to lose basically all of its inertia. On top of that, it's going to bypass around the heat sink. It's just such a high pressure drop. All of the fluid flow inside of the heat sink is going to be buoyancy driven. But that's not to say that we can't learn a few things. You may notice that there are a few data points missing here. Our test setup isn't necessarily the most efficiently set up, so I don't have any pump power curves or excuse me, anything like that. But the reason why we're missing these data points is because we actually maxed out our pump. So some of those like 6 centistoke fluids, we couldn't actually get to 12 liters per minute. That needs to be considered because, again, returning to that argument of regional-based deployments, we may not be able to have one system set up for all. We may need to change things like pumps and heat exchangers and resize some of our system in order to meet some of the fluids. There are certain physics that we just can't get around. We can't lower the viscosity of the fluid without simply changing the flash point. So in terms of our system design and our validation, these are some things that we really need to consider going forward. All right. Now we're looking at an air versus an immersion heat sink. And the use case here is, there are a lot of, there was a question earlier about, when are we going to see immersion-born servers, right? And the nature of that question is maybe the TIMs, but we still need to consider the heat sink. There's very narrow fins that come for air cooling, but what about immersion cooling? When are we going to see those basically loaded on right from the get-go? In some cases you can get that, in many cases you don't. So is it worth the time, the expense, the labor to swap out all of those heat sinks? How much performance are you going to recover in terms of actually lowering the chip temperature or enabling a higher TDP? So the answer is actually quite a bit. You can see up to 25%. But as I mentioned, these heat sinks, there's still quite a ways to go. And I think that's one of the work streams. We've seen a little bit out of it, out of Intel and Mark McDonald's group. They've done a great job with their targeted flow heat sinks. But I think there's still even more that we can do in terms of tailoring some of these heat sinks to the deployments. All right, so next, we've moved on to forced convection. So one more time, this is the flow being pumped directly to the chip. And really what we want to look at here is what is the effect of the flow rate. Certainly you can keep increasing the flow rate. You're going to get some diminishing returns. And so just how much is it worth pumping to each and every chip 9 liters per minute? That's a lot of flow. You're going to get some big pumps. Interestingly, what we see is actually a narrowing of the differentiation between the fluids. You don't see quite as big of a drop from the high viscosity fluid into a low viscosity fluid. But that isn't the whole picture, right? I return to the system argument. Pumping a 6 centistoke fluid at 8 liters per minute is not nearly the same as pumping a 1 or 2 centistoke fluid at the same flow rate. So these are a couple more considerations that we're going to have to look into. And again, trying to validate a setup before deployment is going to be paramount here. So on the right side, we're looking at Reynolds numbers. So 3-second look into non-dimensional analysis. Reynolds numbers, right? It's a ratio of the inertial to the viscous components of the flow. Forgive me, but the reason that I'm putting this up here is a discussion of figures of merit. So we have the figures of merit that were put forth, I think, a year or two ago now, and those are derived from heat transfer correlations in which were appropriate for perhaps a different application. They may be applicable. Certainly they were derived for natural convection, so when it's moved to forced convection, we probably need to reconsider them. But in either case, we can either validate those correlations as we start collecting more and more data, or we can develop new correlations. We already have the Prandtl number, so for those of you with knowledge of heat transfer correlations, you got 3 numbers, Nusselt, Reynolds, and Prandtl. We got the Prandtl number, it's all fluid properties. You can get those from any data sheet. Now we can start measuring the Reynolds number, right? With directed flow, we know the flow rate, we know the heat sink spacing, and so we can actually back out what the Reynolds number is. The last one is the Nusselt number. It's the last bogey we got. So we've got some plans on how to tackle that in the future. Nothing to share today, but I think sort of stay tuned, and I think we have some interesting things coming down the pipeline. But I did want to give a little bit of a insight, little splashes to sort of the direction that we see some of the science-based stuff moving. All right, natural and forced convection. I think this is my last data slide, so forgive the eye charts. So natural versus forced convection, right? What do we see going forward in that move to 1,000 watts, raising the ceiling, all of those things. There is quite a bit of performance to be gained as we go there. But kind of as I said in the beginning, there's actually still quite a bit of runway just in natural convection. So let's not move on from that. We got this nice shiny forced convection. It's wonderful, it's great. There's still a lot of improvements that can be made just in natural convection going forward. All right. I think I'm doing a good job of leaving myself enough time for some questions, but a quick summary, right? So this is a pretty broad data set. What I actually shared with you guys was probably about 20% of the total data that we actually gathered. So there's quite a bit more behind it. limited in time, and I probably would have taken up the whole hour if I tried to share everything. But along the way, we were able to find out a couple interesting things. Natural convection can take us pretty far. Forced convection, there's still a great window of performance out in front of us. And perhaps most importantly is that there actually is fluid differentiation. So although there are many out there, and I don't mean to confuse the problem more, I do want to emphasize that not necessarily all these fluids are going to perform the same. So it's not going to be drop-in replacements one-to-one. We do need to characterize these. We do need to validate the performance before we go into deployments. So in terms of my call to action, there are a few hiccups that we ran along the way. So some things to consider. I mentioned sort of some heat sink design, a little bit more standardization in terms of test equipment and test protocols. I think it'd be one thing. We're all doing our own testing, and just like the other work streams, I think we need to share about that a little bit more. We need to share some data, and I think all of that is going to give us a little bit more confidence in terms of immersion deployments and simply understanding the technology and the direction that it's going. Small shameless plug is that I will be co-leading the Advanced Cooling Methods group. It's a brand new group. We're looking at basically a lot of stuff that I presented today, but as well as more. So please sign up, please join in, and stay tuned for a couple of those email alerts that are coming up, and join the group and contribute. A few others that are relevant that I listed as well, and then our QR code for the immersion group. Thank you, and I do want to acknowledge a couple of people. My co-author, Matt Donahue. This data would not be here today without him, although he's not up on stage to join me. He was a huge contributor. And then I also want to thank the OCP leads and the steering committee for the opportunity to share all this with you. So thank you, and would be happy to take any questions. You got one right here? Yeah, please.
One quick question is, what was the maximum case temperature you were operating with to determine the 700 watts or whatnot?
Yeah, so 83 Celsius. That was what was provided to us from whoever provided the TTV. But that's sort of going to be dependent upon the chipset and things like that you're given, or the chip maker's set. What's I think important is that with TTVs you can really precisely control the power, as well as you can extend it beyond if you were to use an actual chip. And so dialing that in and making sure that you have high quality controls on that is pretty important. But 83 Celsius is the answer. Another one? Yeah.
So the data that you presented, how long did you run it, and what does it mean by steady? In the sense, I'm actually conducting some experiments where I see the thermal interface material getting washed away and settling at the bottom of the tank. And temperatures creep up ever so often. So
Yeah.
What does the word steady mean?
Yeah.
And how do you account for the interface loss?
Okay, so couple questions buried in there. So steady state. Steady state for us means the entire system. So that would be the fluid inlet temperature, the fluid outlet temperature, the power delivery, the temperature on the TTV itself, the temperatures on the heat exchangers, pressures and flows, all staying within 1% of the targets for 5 minutes. And then we collect data for that 5 minutes and then average it. So the differentiation would be no more than 1%, 0.5% for the TTV, and that's the data that I showed. The second part of your question, sort of on the thermal interface material, yes, that is commonly seen. Some of the greases, they're just not compatible with a lot of the hydrocarbon-based fluids. There are a couple solutions out there that are ready off the shelf. So indium foil, I would recommend you look into. For a simple testing environment, it's pretty good to go. I think there are a lot of questions, and I don't want to dabble on it too much in terms of scalability. But indium foil would help you, I think, maintain a good thermal interface material for the duration of your test. Yeah. Got another one question.
Hi, so I really like the fact that you use the Reynolds number
Yes.
to help characterize forced convection, and you talked about how for natural convection the fluid really matters in terms of the performance. So the suggestion is you did it for the Reynolds number, and natural convection you could use the Rayleigh number or the Grashof number to also look at similar performance metrics that way.
Yes, yes, I would love to. And similarly, if you look at the Grashof number, right, you still need the base temperature of the wall that you're using, and that's sort of some of the challenge associated with it is that you would really basically need an instrumented heat sink. That's sort of the part that we're working on. Stay tuned coming forward. But yeah, if we could instrument the heat sink basically and get wall temperatures and heat fluxes, now we can get the Nusselt number, right, or the Rayleigh number or the Grashof number, excuse me, in terms of the natural convection. So yeah, would love to go that direction. We're working on it. I promise you, but it's definitely sort of diving a little bit that extra layer deeper into the heat transfer and approaching non-dimensional analysis. I think is sort of a direction we should go.
Very good. All right, thank you.
Thank you. Question over here. Here, if that doesn't work, you can say it to me and I'll repeat it. Here, why don't you ask your question? I'll just repeat it to everybody.
I have a question about the test rig itself.
Yeah.
I'm wondering if the surface geometry inside the thermal test rig can be modified to mimic the latest design in the server. I mean, I think the flow resistance in your system has a big impact. I mean, as a close related to the surface geometry of the chips or any kind of hardware inside it, and that will have a big impact on flow resistance and also to the Reynolds number that you use.
Yes, I agree. So for instance here, right, you have what basically were the fan ports and things like that, and those represent hydraulic resistance, and so those could be an evening or spreading of the flow. Perhaps if they're not there, right, you could get concentrated flow in one direction or the other. You could get small recirculation zones. So those are things to consider. That is where it's very difficult because we can't represent that for literally every type of server and things like that. So what we were trying to do here, the real aim was as apples to apples as possible in terms of setting the same condition set for all fluids and only parametrically, right, changing one thing at a time. So we could modify it, yes. We can put things in, take things out, absolutely. I think it would just be a nature of what is the direction, what is the motivation for that specific research.
All right, thank you.
Time. Awesome. Thank you. Thank you, everybody.